Deep beneath the ocean surface, production wells release a violent, high-pressure stream of raw hydrocarbons. This turbulent mixture of crude oil, salt water, and volatile gases surges upward through the risers, arriving at the deck of the FPSO at temperatures exceeding 80 degrees Celsius and pressures up to 4,500 kilopascals. Left untreated, this raw well stream is highly corrosive and completely unsellable. The primary objective of the Topside facility is to methodically break this chaotic emulsion apart, isolating it into export-ready crude oil, clean water for safe disposal, and dry gas for power and export. To map how this separation occurs, we will track the fluids through the process modules using a standard color code. The crude oil path is highlighted in green, the produced water in blue, and the separated gas in yellow. Following these three paths reveals the exact sequence of pressure, temperature, and chemical changes required to turn hazardous raw fluids from the ocean floor into highly valuable commodities. Let's trace the flow. Step 1 begins at the topside arrival point. The raw well stream travels up the subsea production risers and enters the inlet manifold. Because the arriving crude can be highly viscous and bound tightly with water, it is immediately routed through a crude inlet heater. Raising the temperature lowers the fluid's viscosity, weakening the surface tension that holds the stubborn oil-water emulsions together. Looking at this cutaway of the high-pressure separator, you can see the initial three-phase separation taking place. The heated mixture enters and slows down. Gravity takes over. The heaviest blue water drops to the bottom, the green oil floats and spills over an internal weir, and the lighter yellow gas flashes to the top. From here, the bulk oil moves into the low-pressure separator. By intentionally dropping the system pressure, the remaining volatile light ends trapped in the crude flash off into a gas state. This pressure drop is the first critical step in stabilizing the crude. At this point, the oil is mostly dewatered, but it still contains microscopic droplets of salt water. To reach commercial specifications, we route this semi-stabilized fluid into the electrostatic treater. Inside this vessel, high-voltage grids polarize the suspended water droplets. The positive and negative charges cause these tiny droplets to rapidly attract and coalesce. As they grow larger, they become heavy enough to sink out of the green oil phase, driving the final water content down to the strict 0.5% target required for export. Finally, the stabilized crude passes through a sales oil cooler, where its temperature is lowered before it gravity feeds into the large cargo storage tanks in the FPSO hull. By manipulating temperature to break emulsions, dropping pressure to flash off gas, and applying electrical fields to extract salt water, the Topside facility safely refines a volatile raw mixture into a stable, export-ready cargo. We've tracked the oil, but the blue water and yellow gas require their own processing before they can leave the facility. The dirty produced water collected from the bottom of the separators is first routed into a skim vessel to settle out the bulk of the residual oil. To remove the remaining oil, the water is pumped into a bank of hydrocyclones. Inside these tapered tubes, a rapid pressure drop forces the fluid into a tight spinning vortex, pushing the heavier water to the outside wall, while the lighter oil is concentrated in the center core and rejected back to the process. The treated water then flashes through a degasser to release any dissolved gases. At this stage, the oil concentration sits below the strict 29 milligrams per liter limit, making the water safe for continuous overboard discharge into the ocean. Meanwhile, the yellow flash gas recovered from the top of the HP and LP separators must be pressurized. We route it through the booster and high-pressure compressors to prepare it for utility use. In this triethylene glycol, or TEG, contactor tower, the pressurized gas flows upward against a steady rain of liquid glycol. The glycol physically absorbs the moisture out of the gas. The result is a highly compressed, completely dry gas exiting the top of the tower. This dry gas is then distributed to 4 potential destinations: fuel for the onboard turbine generators, sent downhole for artificial gas lift, compressed further for reservoir reinjection, or sent to a pipeline for final export. The FPSO also runs a parallel seawater injection system. Lift pumps pull thousands of barrels of ocean water up to the deck, where it passes through coarse and fine filters. The filtered water enters a vacuum deaeration tower to strip out dissolved oxygen before high-pressure pumps force it deep underground. By treating the produced water for discharge, drying the gas, and injecting oxygen-free seawater, these secondary loops maintain environmental compliance at the surface and replace the extracted volume to preserve the structural pressure of the subsea reservoir. Surrounding these main processing lines are 7 essential utility systems. They operate in the background, providing the heat, pressure, and safety controls required to keep the facility running. The flare and vent systems are the primary safety reliefs. If process pressures spike, knockout drums intercept the fluid, capturing liquid hydrocarbon droplets, allowing the gas to be safely combusted at the flare tip. The fuel gas system acts as the facility's power plant, continuously pulling a fraction of the dry, compressed gas we just tracked to fire the onboard turbine generators and compressors. This schematic outlines the closed-loop thermal systems. The red heating medium loop recovers exhaust heat from the turbines to warm the crude inlet heaters. In parallel, the blue cooling medium loop absorbs excess heat from the pressurized gas and sales oil, dumping that thermal energy to the ocean via seawater heat exchangers. To maintain flow assurance, the chemical injection system continuously doses demulsifiers, scale inhibitors, and biocides. These are injected directly into the subsea wells and topside piping to prevent hydrates, scale, and corrosion from clogging the network. The facility utilizes 2 distinct drain systems. The closed drain safely captures pressurized hydrocarbons from equipment maintenance and recycles them back into the process. The open drain collects deck spills and rainwater, routing them to slop tanks to ensure no oil escapes to the sea. Finally, the compressed air and nitrogen systems supply the instrument air needed to actuate the hundreds of automated valves and provide inert blanketing gas for the tanks, while a reverse osmosis unit continuously generates fresh water for the crew. The separation modules generate the product, but the utility backbone supplies the thermal energy, the mechanical power, and the chemical inhibitors that prevent the entire operation from seizing up. When all these systems operate in sequence, the facility functions as a single, continuous organism. The green oil, blue water, and yellow gas flow simultaneously across the deck, balanced by automated controls. A single hydrocarbon molecule arriving from the subsea wellstream is heated, separated, flashed, and electrostatically polished before dropping into the hull as stable, high-grade crude. Every step of that journey is enabled by the utility systems silently cycling heat, generating power, and standing by to vent excess pressure in a fraction of a second. If you need to review a specific module, use the chapter markers to jump back. For a deeper engineering dive into exactly how these valves and sensors dictate the flow, consult your system piping and instrumentation diagrams.